Hi everybody and welcome. Today we're going to be taking a look at identifying zeros of polynomial functions, identifying imaginary zeros of polynomial functions, and taking a look at some of the graphs that happen when polynomial functions have repeated zeros. So a whole bunch of focus on some of the behaviors of these functions that we're going to see, some special cases of when basically everything doesn't work out according to plan. So first, identifying the zero of a polynomial function in factored form. Something that we are familiar with here, we just write the factored form is x minus a. So if a is a zero, x minus it, the opposite sign of it, is our factored form. So what might happen is you might see a zero that repeats. So if it does repeat, then instead of the factored form just being x minus a, it might be x minus a to the k power. So it might happen multiple times. So if it happens twice, k would be to the second power, 3 times k to the third power. So if this does happen, if we see a repeated root, if k is even, then the function touches, but does not cross the x-axis at x equals a. So basically what that's saying is if it's to the second power or to the fourth power, we're actually not going to see this as something that goes across the axis. It'll bump. It'll like bump into it and then just go back the way that it came. So it won't go through it. If k is odd, though, so first power, third power, so on, then the function does in fact cross at x equals a. So in our image below here, what we're going to see is the two different types of root that we might have here. So right here, our first one, this crosses the x-axis, so because it crosses, we know that k is an odd number. But the second type, we might see that it bumps into it and then it goes back. If it just touches it, that's what that looks like there, then we know that k is going to be an even number. So let's say in this circumstance that x equals 4 in blue and x equals 1 in red. Well, if that's the case, then we know that our factored form is going to be x minus 1 just once, or 3 times, or 5 times, as long as it's odd, and then x minus 4 at least twice, maybe more. So let's take a look at Desmos, and let's see kind of what happens when we go through this process. So like x minus 1, x minus 4, and so on. So actually, conveniently, we already have the first part of it done. So x minus 1 is our first root, and then we said x minus 4 is our second one. So if we just do it one time, what we can see is that it crosses through 4, but that's not what happens in the graph that we saw before. It kind of bounced back down. So instead, if we have it happen 2 times, we're going to see that it will, in fact, bump into 4 and then keep going. So again, that's kind of what we're looking for. And let's test it. So we said, as long as it's an even number. So what about 4? Oh, I see the same thing. It bumps into it and goes back. Or 6. But if we did it in an odd number, so 1, as we saw, it goes through it. 3, it goes through it. 4 is an even number, so it bounces off. 5, it goes through it. 7, 9, all of these go through. So that's kind of the idea for bouncing off or crossing through a point. So if you ever look at graphing or you're stuck on any of those, we can use that, basically that rule, and that's going to keep us grounded on what we're looking for. All right, so continuing forward onto imaginary roots. So imaginary roots are basically what happens when Mr. Reardon makes a typo, or maybe the function doesn't work out very well. So when we solve for the zeros of a function, but the number of roots does not equal the degree of the function, then there are imaginary roots. Some imaginary root exists. So how we work through this is we find these imaginary roots, because they're hiding. We have to use some special tools. By utilizing all of the factors that we know, then solving using other methods that we know from the past, something like the quadratic formula is a really good friend. So in our example below for today's practice question, if when we work through this, and I'm saying I've already done it, so you can trust me, you don't have to work through it, but if we did work through this and try to get all those answers, and the only thing that worked that we found was x is equal to 4. There were no other roots. Well, the problem is, based off of what we talked about in class, third power, we expect to see 3 roots. So sad face here, because we only have 1 root, so there must be 2 imaginary roots. So the way that we work through this is we have to use everything that we know to try to solve. So we understand that x is a factor here, so that term that we have is going to help us out. And we need to use this basically to work through and see, can we find anything else? So if we know that 4 is solved for, we can put it there on the side, so x equals 4, and then we can use synthetic division. Just to verify that 4 does work. 1, 2, 26, and then 104. So that actually did work out well. Remainder of 0. Good, so that's what we expected. We wanted to have a remainder of 0. But when we work through this, what we're going to see is we get x squared plus 2x plus 26 with a remainder of 0. So after dividing, that's our answer. And remember, x minus 4, the opposite of that x equals 4 term, is multiplied by it to give us the same thing. So that was one of the ways that we were factoring last week, using the synthetic division, writing the final answer, and then writing our factor term next to the synthetically divided answer. So if we multiply these together, we're going to get back to what's highlighted in yellow there, the original. So what this allows us to do is here's one root right here, and we find that root by setting it equal to 0. Well, we can do the same thing here. So we can set both of these equal to 0. So x minus 4 equals 0, so we got this one already. We know that x equals 4. But the second thing, x squared plus 2x plus 26 equals 0. We can also work through this one. So taking a look here, not factorable using the box method, unfortunately, but we know the quadratic formula. So we can do minus b plus or minus square root b squared minus 4ac all over 2a, and work our way through the steps based off of that. So we know that a is 1, b is 2, and c is 26. And then one step at a time, make our way through the quadratic formula. So start off here, we'll do our exponent, and then we'll also do our multiplication. So I'll have 4 minus 104 all over 2. And then we can subtract on the inside. You got to be careful subtracting here because we have a few negatives. We're left with negative 100 over 2. So if we have a negative square root, reminder that we can turn it into a positive square root, we just have to take I out. So by taking I out, we have ourselves just the root of 100, which we can solve that. So minus 2 plus or minus I times just 10 over 2. And then split this up into its positive and into its negative parts. So we'll have negative 2 plus 10i over 2. And we'll also have negative 2 minus 10i over 2. So a couple things that we can do. Because there is a 2 on the bottom, and 2 does in fact go into each of these numbers, we can utilize some factoring to simplify. So we can see this as, on the top here, 1 plus 5i, negative 1 plus 5i, and then the second one, we can see it as negative 1 minus 5i. And again, the reason for this is we can take a negative or positive 2 out, and then negative 1 plus 5i is what we factor out, and then those 2's cancel. So a nice Fraction Friday question for you there. But the idea here is that we have in fact solved for our 2 imaginary roots. So these are the x equals imaginary root x equals imaginary root. So if we were to write out our full factored form of this, including imaginary roots, we would end up with the final answer of changing that in yellow over to instead our full factored form. So x minus 4 is our first one, and then x minus our first term, which is -1 plus 5i, and then x minus our second term, which is -1 minus 5i. So that would be the factored form of each of these. So factored form, factored form. And from there, last step, distribute in our 1, and we can simplify. So we can distribute in this 1 and simplify. So left with x minus 4, and then x plus 1 minus 5i, and then x plus 1 plus 5i would be our full, final, beautiful answer. So that would be our factored form, including our imaginary roots. So that's the idea for today. We might be jumping into some mostly just factoring questions. So I would say a good knowledge of quadratic formula. If you have a TI-80 series calculator, you can, in fact, program the quadratic formula in. But one downside of it is that the TI-80 series calculators are not going to be as nice with imaginary numbers. So you will still have to do quite a few of these steps by hand. But if we have the steps down and we know what we're solving for, we should be in good shape to be successful. So as always, thanks for watching. Let us know if you have any questions, and